Predicting the extent of a reaction means how much the reaction will proceed in forward direction, how much percentage wise you can say the product will be there, or whether it will hardly proceed, it will proceed to almost completion, or it will be somewhere in between. So for that we compare the value of Kc. If equilibrium constant value is greater than 10 to power 3, that is greater than 1000, then we say that yes, appreciable amount of products will be there. Okay, so the reaction will have substantial amount of products. So products predominate over reactants. Why? Because you know that for this reaction, if I take it as an example, Kc will be given by HCl concentration whole square divided by H2 concentration, Cl2 concentration. In simple terms, I can say it means it is products concentration raised to their stoichiometric coefficient divided by reactants concentrations raised to their stoichiometric coefficient. And if this is greater than 1000, it means the concentration of products is 1000 times concentration of reactants at equilibrium. So it means predominantly we have products here. So you will say the reaction will be almost up to completion, nearly to completion. In this case, for this example, if you see the value of equilibrium constant, it is 4 into 10 power 31. It means the product's concentration at equilibrium will be 4 into 10 to the power 31 times approximately to reactants concentration. Very, very high concentration of products. Hardly there will be any reactants at the time of equilibrium. So it will almost complete to 100%. Next one, suppose Kc is less than 10 to the power minus 3. That is, Kc is less than 1 by 1000. We apply the same approach. Kc is given by products concentration raised to their stoichiometric coefficient divided by reactants concentration. And if it is less than 1 by 1000, it means here reactants concentration is 1000 times of products concentration. So hardly any products will be there. It means hardly any reaction happened there. So in this case, we will say reactants predominate over products. Kc is very small, reaction hardly proceeds. This is an example of that. Nitrogen and oxygen can combine to produce nitric oxide at room temperature, that is 298 Kelvin, but there is hardly any reaction. The Kc value is 4.8 into 10 power minus 31. So hardly any reaction will take place. Then suppose Kc is in between 10 power minus 3 and 10 power 3, then we will say yes, there is something, some amount of reactants is there, some amount of product is there. What we say here, appreciable concentrations of both reactants and products are present. That's what you will write if you are asked what do you understand if the value of Kc is say 100, Kc is 57. For example, for this reaction, when hydrogen and iodine react to produce hydrogen iodide, the Kc value is 57. Okay, so you will say yes, appreciable amount of both reactants and products will be present. Diagrammatically, this is the way you can understand. This is the limit. If it is less than this one, negligible amount of product. If it is greater than 10 power 3, appreciable amount of product. So in this case, reaction hardly proceeds if it is less than 10 power minus 3. If it is greater than 10 power 3, reactants are almost negligible. We have mostly products there. So reaction proceeds almost to completion. Then we talk in terms of the reaction quotient also. Remember, this is equilibrium constant. Okay, this is equilibrium constant. This is reaction quotient Q. They both have the same formula. And why I am using it? Because at equilibrium, the concentrations will be constant. After that, they will not change. Okay, but suppose I start the reaction, H2 plus I2 will give you 2Hi. I start this reaction with H2 and I2, and it has not reached equilibrium. Suppose it starts from here, and to reach equilibrium, this is the point, this much time to reach equilibrium. But suppose reaction is here. then how I can say that yes, reaction is here, it has not achieved equilibrium? Or suppose I start from HI side. If I start from HI side, again the reaction will proceed towards equilibrium, same equilibrium, but now it is from the reverse side. And say at this point I have some concentrations of hydrogen, iodine, hydrogen iodide. How would I say that whether it is at equilibrium or not, considering the concentrations of all the reactants and products at that point of time? That is the question which will be asked. Question will be, at any point of time, these are the concentrations of all the reactants and products. Tell whether the reaction is going in forward direction, whether it is going in backward direction, or whether it is already at equilibrium. So suppose here some concentrations are given of H2, I2 and HI. Here some concentrations are given of H2, I2 and HI. When reaction is happening, obviously all three will be present there. And there will be some concentration H2, I2 and HI at equilibrium also. At equilibrium, these concentrations will not change and will give me constant value, which is known as equilibrium constant. So equilibrium constant for this reaction, if I am talking about, Kc will be product concentration raised to its stoichiometric coefficient divided by reactants concentration raised to their stoichiometric coefficient. Okay. Now what I do, here also I can have the same ratio, but that will not be called equilibrium constant, because at that time the concentrations are not constant, the reaction is happening, okay, effectively in any one direction, either forward or reverse direction, net reaction. So the forward rate will not be equal to reverse rate at that time. So the same ratio here I can calculate, and from that I can find out whether the reaction is going in backward direction or forward direction. But here now I will call it QC, reaction quotient. I will not call it equilibrium constant because it is not constant. Here also I will call it QC. So the same ratio at any other point of time other than equilibrium is called QC. Then I can compare QC and Kc. So for a reaction, Kc is given. So for example, for this one, Kc will be given as 57. So we know that this is already calculated. For this reaction, the Kc will always be 57 at room temperature. So suppose we calculate the value of Qc with the given values of hydrogen concentration, iodine concentration, hydrogen iodide concentration at a given point of time. Then if Qc comes out to be equal to Kc, then we will say yes, the reaction is already at equilibrium because both of these ratios are equal. But suppose these are not equal. Suppose the case is Qc is less than Kc. Then what's the status, where the reaction is? Suppose if we start from H2 and I2 and we start from HI, the reaction equilibrium is achieved, say here, this is the equilibrium point. So whether we are here or whether we are here, this is very easy to calculate, because QC or Kc is actually products concentration divided by reactants concentration. If QC is less than Kc, okay, so suppose it is now P dash and R dash concentration, okay, QC, it is less than Kc, it means it is 100% sure that this P dash is less than P, numerator is less, or otherwise you can say reactants concentration is greater than R. Okay, so at this point of time, reactants concentration is greater than the reactants concentration at equilibrium. In any case, the value of QC will be less. So remember, it means if QC is less than Kc, this tells us that products concentration at this point of time is less than products concentration at equilibrium. So if products concentration is less, obviously it means it is going in forward direction. it will achieve equilibrium when we have the concentration P, concentration of product P, then it will be equilibrium. So at this point of time, if the concentration of products is less than P, which is equivalent concentration, it means the reaction is going in forward direction. So if QC is less than KC, it means the reaction is proceeding in forward direction. And this is very easy to understand with this diagram. Okay, if QC is less than KC, then you will draw the arrow like this. So it is always try to achieve KC. So QC will move towards KC. So QC here will try to move to KC. It means the reaction is going in forward direction. Otherwise, if QC is greater than KC, it means product's concentration is higher, and product's concentration is higher than equilibrium, means it must go in reverse direction to achieve equilibrium. So it means it will proceed in reverse direction. This is the way you will identify whether the reaction is going in forward direction or reverse direction at any point of time. Question will be very simple. This is the value of Kc. These are the concentrations at any other point. Specify whether the reaction is going in forward direction or reverse direction. So we have this example for that. Kc is given for this reaction. Kc is given. Kc is given. Now at any given time, it might be equilibrium, okay, but this is any point during the reaction. The concentration of A, B, C are 3 into 10 power minus 4 each. Then tell the direction of the reaction. So what you will do, you already know Kc is given. Kc is 2 into 10 to the power minus 3. You need to calculate Qc with the given concentrations at that time. So you will say Qc will be product's concentration raised to their stoichiometric coefficient divided by reactant concentration raised to its stoichiometric coefficient. Now, even if you don't substitute the values, if you know that all of these are equal, this will be 1. Okay, all these are equal. Here also you will get a square, and here it is already square. You will get 1. In exam, obviously, you need to first write the values and then get the value 1. Here you can say Qc is 1, which is obviously greater than Kc, which is 2 into 10 power minus 3. So if Qc is greater than Kc, it means the reaction is going in reverse direction. So you must remember these things. Qc is less than Kc, forward direction. Qc is greater than Kc, reverse direction. Equal obviously is equilibrium. Next one, 3 moles of PCl5 kept in 1 liter closed reaction vessel well allowed to attain equilibrium at 380 Kelvin. Calculate composition of the mixture at equilibrium. Kc is given. Composition of the mixture means you need to calculate the equilibrium concentrations. At equilibrium, whatever is the composition, that is concentration. Concentration means molarity you have to calculate. And this question requires your mole concept knowledge as well. So first you will write the reaction. PCl5 dissociates into PCl3 and Cl2, chlorine. And then you will say at equilibrium, initially you have 3 moles of PCl5. So when the reaction has not started, products will be 0. Then suppose you say that the change which has taken place to reach equilibrium, suppose X moles of PCl5 consumed. Then how many moles of PCl3 and Cl2 will be produced? That will be decided by balanced reaction. This is the balanced reaction, and you see the ratio is 1 mole here, 1 mole here, 1 mole here. So it means 1:1:1. So it means if X moles are consumed, you will get X moles of PCl3 produced and X moles of Cl2 produced. Ratio is 1:1:1. So 1 mole of PCl5 gives you 1 mole of PCl3 and 1 mole of Cl2. So if X moles consumed, X moles will give you X moles of PCl3 and X moles of Cl2. It means at equilibrium, how many moles will be there of each? This will be 3 minus X, 3 initial and X consumed. This will be 0 plus X, this will be 0 plus X. This is the equilibrium condition. 3 minus x moles of PCl5, x moles of PCl3, x moles of Cl2. Now Kc is given, apply the formula. Concentrations you know in terms of x, 3 minus x, x and x. You will write Kc for this reaction will be product's concentration raised to their stoichiometric coefficients divided by reactant's concentration raised to their stoichiometric coefficient. Product concentration x into x, both have x, and here PCl5 has 3 minus x. And it is given Kc is 1.80. So from here you will get quadratic equation. Quadratic equation you can solve. You know that the quadratic equation roots are minus b plus minus a square root b square minus 4ac divided by 2a. Okay, so quadratic equation. That's what you will do. So just explaining it with detail. You have initial concentrations, then this is the change, then this is at equilibrium. You apply the equilibrium constant formula, substitute the values, get the quadratic equation, solve it. Here you will get two values obviously of x. You will discard negative value because concentrations cannot be negative. Here you see this is the concentration. X is concentration of PCl3, Cl2. This cannot be negative, so you will discard that value. So you will select the positive one. You will get x equals to 1.59. And the moment you have these values, you can calculate the concentrations. Concentrations will be PCl5 concentration will be 3 minus 1.59. PCl5 will be 1.59, Cl2 will be 1.59. These are the answers. These are the molarity basically. Next question. Very important one. Okay, if you can understand this one, many such questions you can solve. This one is really important. 13.8 gram of N2O4 was placed in a 1 liter reaction. Another point which I did not explain in previous question. Just I'm going back. Okay, here it is given 1 liter closed reaction vessel. That's why I considered these 3 moles as molarity. You remember the molarity is number of moles divided by volume. Because it was 1 liter, so number of moles 3 divided by 1, it will be 3. The molarity will be 3. Otherwise, to get the molarity, I will divide the number of moles by volume. So suppose instead of 1 liter, it was 4 liters. In that case, I cannot use 3 here. Okay, in that case, I cannot use 3 here. If it is 4, then it will be 3 divided by 4. Number of moles divided by volume in liters. Those many moles means 0.75 moles. So the calculations would have been different there. And it is good to write, even if it is same, it is good to write that you write the molarity will be 3 by 1. Number of moles divided by volume equal to 3 and then use it. In this question also, 1 liter. Okay, so the volume is 1 liter. Whatever the number of moles we will get, that will be the molarity. But here, number of moles are not given. Grams are given. And you know that you can convert grams to moles. Given mass divided by molar mass. Reaction is given at 400 K. The total pressure at equilibrium was found to be 9.15 bar. Remember, we can do calculations in terms of concentration, that is the molarity, or in partial pressures also. So specifically here, the concentrations are in terms of partial pressure. That's why we are talking about bar here. So total pressure, it is pressure of both N2O4 as well as NO2 total at equilibrium is given. Calculate Kc, Kp and partial pressures. In this case, because we are talking in terms of pressures, concentrations in terms of pressure, we cannot calculate Kc first. Okay, first we have to calculate the partial pressures. Why partial pressures? Because we will use those partial pressures to get Kp. Why? Because Kp for this reaction will be partial pressure of NO2, concentration of products raised to their stoichiometric coefficient 2 divided by reactant's concentration in terms of partial pressure, that is partial pressure of N2O4 raised to its stoichiometric coefficient, which is obviously 1 here. So to calculate Kp, first we need partial pressures, and partial pressures are asked. Even if it is not asked, you have to calculate. Okay. So first calculate partial pressure, get Kp, and then apply Kp equals to Kc RT to the power delta Ng. That will give you Kc. So how to get the partial pressures? Again, apply the mole concept formula there. Okay. To get the number of moles first, we will get the molar mass of N2O4, so that we get given mass divided by molar mass and we get the number of moles. So molar mass of N2O4 is 92. How do you calculate? 2 into atomic mass of nitrogen plus 4 into atomic mass of oxygen. You will get 92. Okay. Number of moles will be given mass divided by molar mass. So you have 0.15 moles of N2O4. Okay. Then we know PV is equal to nRT. PV is equal to nRT. So P into 1 liter. Remember, we are going to do calculations in terms of pressures. Here we have pressure, so we can't use number of moles. That's why I made it clear. The calculations have to be in pressures. So we will convert these number of moles, that is 0.15 moles, into pressure. So these many moles of gas N2O4 will create how much pressure we can get from this equation. PV equals to nRT. Substitute the values. Pressure we need to calculate. Volume is given 1 liter. Moles we have calculated. R we will use 0.831. We will be doing calculation in bar because here it is given in bar. Because total pressure is given in bar, we will use the value of R, which is for bar liter per mole per Kelvin. Temperature is given 400 K. Substituting these values, you will get the partial pressure as 4.98 bar. Means initially, when the reaction did not happen, when we had 13.8 grams of N2O4, these many grams, which are actually 0.15 mole, created 4.98 bar pressure. So initially this was the pressure. Obviously there was no NO2, no pressure contributed by NO2 at that time, 0 moles of NO2. So the entire pressure, initial pressure, was due to N2O4. Now we'll apply the same approach what we did in previous question. Initially, what the partial pressures were there, then what is the change in partial pressure during the reaction to achieve equilibrium, and then at equilibrium, what is the partial pressure. So this is the reaction. Initially 4.98 bar from 13.8 grams of N2O4. We don't have NO2, that's why 0. Percentage change basically, not percentage change. So instead of just writing here directly, you can say that suppose the change to achieve equilibrium here minus X pressure. You can write P also, because we are talking in terms of partial pressures. You can write that the decrease in partial pressure is P. Then the ratio here, now it is not 1:1. The ratio is 1:2. Here you have 1 mole, here you have 2 moles, both gases. 1:2. It means 1 mole of N2O4 will produce 2 moles of NO2. So if P moles of N2O4 are used, these will produce 2P moles of NO2. Or in terms of pressure, if there is decrease of P bar in partial pressure, then 2P bar will be created by NO2. Okay, I will continue with X. It is easier. So instead of P, I am writing here X. So this is decrease in partial pressure, this much consumed, and N2O4 will get consumed. So there will be decrease in partial pressure. At equilibrium, it will be 4.98 initial minus final. And then this one. Okay, so if you consider the equilibrium, 2 times partial pressure will be created by NO2. So what will be the total pressure at equilibrium, which is given? If I go back to the question, it is given that the total pressure at equilibrium is this much, and total pressure will be by both, means the sum of these two is 9.15. Add these. When we add these, we get the value of X, which is 4.17. The moment we get 4.17, substitute these values here, we get the partial pressures of N2O4 and NO2. So substituting these values, partial pressure of N2O4 is 4.98 minus 4.17, that is 0.81 bar. And for NO2, it is 8.34 bar, twice of 4.17. So first part done, which is actually the third part of the question, but the way we need to proceed, first we have to calculate partial pressure. So partial pressure is calculated. Now you can substitute those values here in the formula of Kp. So get the value of Kp. Kp will be partial pressure of NO2 whole square divided by N2O4. Substitute the values. Okay. Then apply Kp equals to Kc RT to the power delta Mg. So N2O4 gaseous gives us 2 moles of NO2. That's why this is the value of Kp. Okay. What will be the value of delta Ng? Delta Ng will be products gaseous moles. So you have NO2 gaseous, so 2 moles, minus reactants gaseous moles 1, that is plus 1. So substitute these values. Get the value of Kc. Remember, because we are using pressures in bar, R has to be 0.0831. Instead of writing 0.0831, you can write 0.083. That won't make much difference in the answer. So Kc you will get 2.6. Now relationship between equilibrium constant K, reaction coefficient Q, and Gibbs energy G. Gibbs energy is same what we have talked about a bit in thermodynamics as well. Okay, this is the free energy of the reaction. This is actually the energy which the reaction has to overcome to be spontaneous. That's why we say that delta G has to be negative for any reaction to be spontaneous. So what is the relationship? If delta G is negative, we say the reaction is spontaneous, means it will proceed in forward direction. If delta G is positive, then obviously the reaction is non-spontaneous in forward direction, but it means it is spontaneous in reverse direction. Okay, so the reaction is non-spontaneous. It specifically means in forward direction. The reverse will be that in reverse direction it will be spontaneous. So instead, as reverse reaction would have a negative delta G, the products of the forward reaction shall be converted to the reactants. The reverse reaction will take place. Delta G is 0, it means the reaction is at equilibrium. Okay, reaction has achieved equilibrium. It cannot go into forward or reverse direction because both the rates are equal at equilibrium. Mathematical expression of this thermodynamic view of equilibrium can be described like this. And remember, you don't need to prove it. You're not going to prove it. You need to use it. Delta G is equal to delta G naught plus RT ln Q. Delta G is Gibbs energy. Delta G naught is standard Gibbs energy. When we say standard Gibbs energy, means it's absolutely free energy at 1 atm or 1 bar. The correct definition is 1 bar. But sometimes in books you will get it written as 1 atm also. Okay. There's hardly any difference between 1 atm and 1 bar. So that doesn't make much difference. Okay. But by definition, if we are doing calculations at 1 bar, then it is called standard. RT, they have their usual meaning, and this is log Q at base E. ln Q means log Q at base E. Normally we have log Q, for example. If we don't write, it is base 10. If we write ln Q, it means it is base E. And there is a relationship between log base 10 and log base E. Normally in calculations, you will use log base 10. Okay, so you will almost always convert log base E to log base 10. When you convert it, suppose there is log A base E, then it will be 2.303 times log A at base 10. The log tables, if you are provided with in the examination hall, those will have the values of log at base 10, not at base E. So remember, you have to use 2.303 times log A. You need to convert for calculations log base E to log base 10. At equilibrium, when delta G is 0, then in that case, Q is equal to Kc. We have talked about QC is less than Kc or QC is greater than Kc. Then obviously they are not at equilibrium. At equilibrium, Q will be equal to Kc. So if it is equilibrium, we can modify this reaction, this equation. We can say that in that case, this Q is Kc and this delta G has to be 0 at equilibrium. So we will get delta G naught equals to minus RT ln K. delta G naught equals to minus RT ln K. This gives us some information. This also gives us some information about when the value of K is 1 or less than 1, greater than 1, okay, then how much the reaction will proceed in forward direction or not. First of all, you need to remember this relationship as delta G naught equals to minus 2.303 RT log K. So in numericals, you will write this formula directly. You will not write ln K. You will write 2.303 log K. This is I am using here just for explanation purpose. Because I'm gonna explain how it will depend on the value of K. That's why. So suppose this is the case, then taking anti-log of both sides, we get this much. Now you might be surprised. How do we get this one? For that, you should have some knowledge of log. When I talk about log, okay, suppose I say log 100. Okay. Log 100 is 2. It is actually log 10 to the power 2. Here it is base 10. I am not writing. Whenever I am not writing, it means it is base 10. Log 100 is actually log 10 to the power 2, which is 2 log 10. Okay. How do you get it? So if you see, there is some relationship. The relationship is, if I write it here, log 1000 equals to 3. What I am saying basically, I am saying I will get this value if I have 10 to the power this value. I will get this value if I have 10 to the power this value. 10 to the power 3. 10 to the power 2. Okay. And from where I got this 10? This 10 is actually the base. So the relationship, if I write it just in general, A, B, C, if I write it like this, okay, the relationship will be this A will be equal to this B to the power C. This is A, 1000 will be 10 to the power 3. This is what I can write. A will be equal to B to the power C. Now consider this one. This one. This is actually log K base E. ln K is log K base E equals to, I am calling this one just X. Okay. Later on I will change it. I will replace it by this amount. It means I am saying here K is equal to E to the power X. Apply the same analogy here. K is equal to E to the power, base to the power, whatever is on the right hand side. That's how you got K equals to E to the power minus delta G naught by RT. So for that, you should have the knowledge of log. So I got K equals to E to the power minus delta G naught divided by RT. This gives us some insight. If delta G naught is less than 0, if this value is less than 0, means it is negative, then this negative and this negative multiplied will give you a positive value. It means this whole power is positive. E to the power is positive. If it is positive, means K will always be greater than 1. K will always be greater than 1. Why? Because if it would have been E to the power 0, then the value would have been 1. You know that any number to the power 0 except 0 to the power 0. So 0 to the power 0 is not defined. You know it from your math. But otherwise, whatever to the power 0 will always be 1. And if it is greater than 0, obviously it will be greater than 1. The value will be greater than 1. So K will always be greater than 1 if delta G naught is less than 0. What it tells us? It means a spontaneous reaction or the reaction which proceeds in the forward direction. If K is greater than 1, it means product's concentration is greater than reactant's concentration. So reaction will proceed in forward direction. Now suppose delta G naught is greater than 0. It means this hole is negative. Now the power is negative. If power is negative, K is less than 1 now. If K is less than 1 means the reactant concentration is greater than product, means the reaction is non-spontaneous. Rather, it might be spontaneous in reverse direction. Okay. It might have gone into forward direction, but very, very small degree. So that's what is written here, which implies a non-spontaneous reaction or a reaction which proceeds in forward direction to such a small degree that only a very minute quantity of product is formed. Because if K is less than 1, it means we are saying product's concentration divided by reactant's concentration is less than 1. We are not saying that product's concentration is 0. We are saying product's concentration is less than reactant's concentration. So the reaction might have gone in forward direction, but up to very small extent. So remember, if K is less than 1, that's why we say that the reaction has gone into forward direction, but up to very small degree. Now the question. Hydrolysis of sucrose gives glucose and fructose. More about it in detail we will be talking about in biomolecules chapter in 12th. Sucrose hydrolysis gives us glucose and fructose. Equilibrium constant Kc for this reaction is given. Calculate delta G naught at 300 Kelvin. So you know the relationship, right? At equilibrium, you know the relationship when it is Kc, okay, which is delta G naught equals to minus RT ln Kc, and I said in numericals you won't use this one, rather you will use this one. Delta G naught equals to minus 2.303 RT log Kc, always base 10. Substitute the values, okay. Kc is given, delta G naught is to be calculated, R and T you need to write. Now here sometimes students get confused that what the value of R I need to use here in this particular case, okay. So in all such cases, 8.314 joule per mole per Kelvin. Obviously that will decide the unit of delta G also. Delta G will also be in joules, okay. Otherwise you need to change the units. If it is asked in bar, delta G naught is asked in bar liter or ATM liter. Remember, the unit of energy is joule or ATM liter or bar liter. That's why in place of joule we can write ATM liter also, bar liter also, but the value of gas constant will change in that case. Accordingly, you will write the unit of delta G naught also. When we calculate, substitute the values and calculate, we get minus 7.64 into 10 power 4 joule per mole. Suppose you use here 0.0821 and then the unit will be ATM liter per Kelvin per mole. In that case, here instead of joule you will write ATM liter. So in that case it will be ATM liter per Kelvin per mole, okay. Not per Kelvin, only per mole, because Kelvin will get cancelled with this temperature here, only per mole. If you use 0.0831, then it will be bar liter per mole. So depending on the value you use, you need to write correct unit. So this is unit of energy, this is unit of energy, this joule is unit of energy. Next question. The value of delta G naught for phosphorylation of glucose in glycolysis is given. So delta G naught is given and Kc is asked. Again you will apply the same formula, okay. Apply the same formula, get the answer. The only point here is delta G naught is given in kilojoules per mole. Kilojoules per mole. So you have to convert it into joules. Or otherwise what you need to do, you need to use R as 8.314 and then into 10 power minus 3. Whatever way you want to do. So you can convert R into kilojoules instead of joules, or you convert this into joules. Substitute the values, get the answer. So log Kc will be minus 2.418 and the anti-log value will be given to you in the examination, or the log table will be given, anti-log table will be given, which you need to use. You will get the value of Kc as 3.81 into 10 power minus 3. Okay. In such cases where you don't know the reaction has not been given, it is fine that you don't write the unit of Kc. Okay. Otherwise, the unit of Kc, if the reaction is given, will depend on the values you have on the right hand side, left hand side, right? On that. Not the values, the components. Okay.